Hello, welcome to 3.8, Newton's method. So Newton's method is a technique for approximating the real zeros of a function. This technique uses tangent lines to approximate the graph of the function near its x-intercepts. So, Newton's method for approximating the zeros of a function, let's f of c equals 0, where f is differentiable in the open interval containing c. Then to approximate c, use the following steps. Make an initial estimate, and this is what your calculator tends to do. This is one of the programming techniques, is to churn out those zeros. Okay, so make an initial estimate of x1 that is close to c. A graph is helpful. Determine a new approximation. The new one is going to be the old one minus f of x over f prime of x, or x sub n minus f of x sub n over f prime of x sub n. And it's really useful to put this type of thing in the calculator and make a table. And if you'd like, I can put together a little video where we do that. If the absolute value of x sub n minus x sub n plus 1 is within the desired accuracy, let x sub n plus 1 serve as the final approximation. Otherwise, you return to step 2 and calculate a new approximation. Each successive application of this procedure is called an iteration. So it's nice to do it in a few iterations. The thing is, the calculator can do a bunch of iterations very quickly. So here we're going to complete 2 iterations of Newton's method for the function using the indicated initial guess. So we're going to guess that 3 is going to be a 0. Well, we know 3 is not a 0. What is the 0? Everyone say it. What is the 0 nearest 3 for sine? Think radians. And if you just said pi, you're right. So we're going to see get close to pi. So we're going to start off with, what is f of 3? That's the sine of 3. And that's going to be 0.14112. F prime of x is cosine of x. So f prime of 3 is cosine of 3, which is negative 0.9900. So our x2, the second one, is going to be our first guess, x1 minus sine of x1 over cosine of x1. So our x2 is going to be, our initial guess was 3 minus sine of 3 was 0.14112. Over cosine, which is negative 0.9900. That's going to be 3 minus negative 0.1425, which is 3.1425. Hey, that's a pretty good jump to pi. That was pretty good. So now we'll go to x3. That's going to be this answer, 3.1425 minus sine of 3.1425 over cosine of 3.1425. And again, sine's the original function, cosine's the derivative. This is going to be 3.1425 minus 0.0009, which is 3.1416. 3.1416 is really close. It's 3.14159, and it goes on forever, obviously. So, to fill in the chart here, we did 2 iterations. There we are. To fill in the chart, f of x sub n was 0.14112. F prime of x sub n was negative 0.9900. Do the fraction there, the quotient between them, that's going to be negative 0.1425. And then x sub n minus that was this result here, 3.1425. Go to the next iteration. This value comes down here, 3.1425. F of x sub n, plug this in, sine of this value is going to be negative 0.0009. And cosine of this value is negative 1.000. The quotient is going to be 0.0009, just this divided by that. Then x sub n, this value minus this quotient, this value minus this number here, is our 3.1416. And that is 2 iterations of Newton's method. Let's go on to the next page. Approximate the zeros of the function, use Newton's method, and continue the process until 2 successive approximations differ by less than 0.001. Then find the zero, or the x, using a graphing utility and compare the results. So I did use it here, and I think this is the value there. No, this is we're close here. We're pretty close. We're not. We'll start there at negative 1.5. So we'll say x1 is negative 1.5. So in the graph we have y1 is x cubed plus 3, and the y2 is going to be 3x squared. That is, this derivative is 3x squared. And that's how I built my chart here. I make a y3, which is going to be this one divided by that one. That's x cubed plus 3 over 3x squared. So I'm building up this table. So I have these values, and these values will line up. So here's y1, y2, y3. I make a y4, which is going to be our initial value, x minus x cubed plus 3 over 3x squared. This is my y4 column. So I'm putting these in, y1, y2. I clear all the other y's out. I'm putting these in. So when I go to my table format, when I go to table, I can just plug in the value, and it feeds them all out. And then my y5 is going to be the absolute value of this value. So it's ABS in the calculator of x minus x cubed plus 3 over 3x squared minus x. So y5 will just be, these go away, absolute value, and the negative doesn't matter. Just say x cubed plus 3 over 3x squared. So this is my y5. So this is what I'm putting in the calculator to get these values. So when I type in 1.5 and I go in the table format, I type in 1.5. Table is the F5 when you're in the graph mode. It fills the rest of these in. Boom, 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 boom. So this becomes negative 0.3750. This is 6.7500. This is negative 0.05556. Here we're doing this value minus this value, double negative, so sorry, it's negative 1.5. So it's going to be negative 1.4444, and the absolute value of the difference is 0.05556. And really this value, this column here, is just the absolute value of this column. So we take this one, plug it in here. Negative 1.4444. Again, we're trying to get closer to the 0, trying to get to that 0. So now we're negative 1.444. We're not quite at the 0 yet. F of this value, so put in the original function, is going to be negative 0.03144. F prime of this value, so plug that in here, is going to be 6.2589. The quotient, this one divided by that one, is negative 0.0021. X sub in this value minus this value is going to be negative 1.4423. And the absolute value of the difference is just, this 0.0022. Moving on, this value comes over to here, negative 1.4423. Plugging this into the original function, negative 0.0003. See, we're getting really close to 0. and then take the first derivative, or plug it into the first derivative. That's 6.2407. The quotient is negative 0.00005. X sub n minus that value is negative 1.4422. The absolute value is 0.00005. And we have to be close to 0.001. We're definitely here. We have that tolerance. So the value we go with here, x equals negative 1.4422. That's the one we go with. Now when I put it in my calculator, if I put it in my handy dandy calculator, and I say, okay, find me a 0. Nope. So F2 on my handy dandy calculator, find me a 0 for x cubed plus 3, comma, for x. And it says negative 1.4422496. So look at that. We're there. It has a little bit after that too, but we're there. 4 decimal places. Pretty cool. If I scroll this up a bit, so feel free to pause if you want to write that stuff down some more. Here it is, having the graphing utility find the 0. Negative 1.44225. Okay, in the first 2 examples, the approximations approach a limit. The sequences converge to a value. If we can define the limit of the values x1, x2, x3 through xn to be c, it can be shown that c must be a 0 of f. So Newton's method does not always result in a convergent sequence. Since the technique relies upon division by the derivative, if the derivative is a 0, it'll fail. When this happens, we choose a different x1, and we choose a different starting place. Let's go on to page 3. Use Newton's method to obtain a general rule for approximating the required radical x equals the square root of a. So I think it's reasonable to say x squared equals a, and that x squared minus a must be 0. So f of x would be equal to x squared minus a. Now we have a function, and f prime of x is 2x. So x sub n plus 1 is going to be equal to x sub n minus f of x sub n over f prime of x sub n. So in terms here, x sub n minus x squared minus a over 2x. Okay, so our x, I should call it x sub n squared minus a over 2x sub n. Okay, so if I say x sub n plus 1 equals 2x sub n over 2x sub n times x sub n over 1, I'm dealing with this, trying to get a common denominator, minus x sub n squared minus a over 2 times x sub n. I'd have 2 times x sub n squared over x sub n minus x sub n squared minus a over x sub n, 2x sub n. Forgot those 2's. Bringing these together, we have 2 times x sub n squared minus x sub n squared. Distribute the negative plus a over 2 times x sub n. We have x sub n plus 1 equals x sub n squared plus a over 2 times x sub n. Now you can take this a step further if we want, and we would have x sub n squared over 2 times x sub n plus a over 2 times x sub n. And that'd be x sub n over 2 plus a over 2 times x sub n. So there's a general formula. The next term would be x sub n over 2 plus a over 2 times x sub n. So there's our formula. Feel free to pause it if you'd like. We're going to go on to the last problem from this section. We're going to use this formula now. Use the results of example 3 to approximate the indicator radical to 3 decimal places. So here's the rule. I rewrote it. I used I instead of n. Doing square root of 7, that's our A. Our A is 7 in this case. It should say A, not Z. So it's x sub I plus 1 is x sub I squared plus 7 over 2xi. That's like x1. So x2 would be x1 squared plus 7 over 2x1. So if we start with, first of all, is it reasonable to say 2 is less than square root of 7 less than 3? Yes, because 2 squared is 4, 3 squared is 9. It's going to fall in between. So if we start at x1 being 2, x2 would be 2 squared plus 7 over 2 times 2. That's 4 plus 7 over 4, 11 over 4, which is 2.75. So then we start off, the first one is a 2. Now we have 2.75. So our x3 is going to be 2.75 squared plus 7 over 2 times 2.75. And that's going to be 2.64773. Okay. Let's look at x4. That's going to be 2.64773 squared plus 7 over 2 times 2.64773. And that's going to be 2.64575. And then we'll take this value and get the fifth one. x5 would be 2.64575 squared plus 7 over 2 times 2.64575. And that would come out to be 2.64575. So out to 5 decimal places, that hasn't changed. I think we can go with that the square root of 7 could be approximated by 2.64575. And the square root of 7 from the calculator is 2.64575. Look at that. Okay, and that'll do it for 3.8, Newton's method. Okay, I hope you guys like that. Give some other uses for derivatives and some ways to approximate things. Thank you.